Mm. Mm. Mhm. Mhm. All right, I see people are slowly going in. We'll wait a couple of minutes to make sure enough people have joined. If you can see it in the chat, I posted a link to the website. If not, please let me know and I will repost. So that website has all the information, for the using, all the slides, installation, and the labs we'll be going through.
I could go visit my cousin while if we go.
So let's give it a couple of more minutes. Looks like we have quite a lot of people here. And then I posted a link to our website. It has all the information you should need for this workshop. It has installation of the packages we'll be using and links to the slides and the labs. So one thing I would encourage you to now, if you haven't already, is to install the packages. It might take a little while, and then we're ready for when the labs should be there. And I'll go ahead and share. Oh no. I'll be back in just a second. I should be having the screen sharing issue fixed. All right, it appears like it's working. So I'm gonna slowly be starting. Here, just showing the website again, zooming in for the measure. And yeah, so it has a little bit of what it's about, of the installation. You just click up here, this little thing, copy the whole thing, and that hopefully should just run. If not, we will take care of that during our first lab. We have links to the different slides we'll be going over. And lastly, we have a link that hopefully should pop up to give you a download to a Markdown file we will be working through together in the labs. So I'll get started with the first set of slides. So before we really go into this, just the certain ground rules of how everything will be working. Overall, we'll be working in a 45-15 schedule. So we'll be doing things for 45 minutes, take a 15-minute break, time for you to get up, stretch your leg, get something to drink, go pee, get some food, and revitalize the brain so we're ready for another 45 minutes. So we're doing 45-10, 45-10 until the end of the session. And I'll try to stop as best as possible at the 45-minute, regardless of where we are in the slides, to make those breaks more consistent. Then we have, as you saw on the website, we have 5 slide decks, and the different slides are all end with a lab session itself. And I had a quick question about and as these people are asking in the chat, you're highly encouraged to ask questions, especially like doing. If you want the direct repository, I just posted it in the chat. Repository itself doesn't have a lot. Mainly what happens is a bunch of some slide files in there, enough to make the website, and then in the folder, the labs file. So if you look at that. So without further ado, let's get started. So this is a workshop of machine learning using tidymodels, and I thought it would be appropriate to start working through a small introduction of what tidymodels is. My day-to-day, I'm a software engineer at a studio, working primarily on tidymodels development. All right. So the goal of this workshop is we want to introduce tidymodels and how we think about modeling in a more general sense and how we're using tidymodels to accomplish those goals, and then help you to become proficient with the core packages. Throughout today, you will learn that there's a vast array of different packages that all have to trace back to a small core of packages. And you knowing this core of packages allows you to expand in the direction you need by using these add-on packages. And lastly, since we can't do everything in a short amount of time as we have today, I'll try to point to different places and more things as we go. So the first big question is, why tidymodels? And it's a very good question because there is a lot of other frameworks that we can use. We have, and they all try to solve more or less the same thing. Tidymodel specifically tries to create a uniform and cohesive set of packages that tries to be as unsurprising as possible. We are a firm believer of the pit of success, meaning that we want you to do the right thing. Like, we want the tools to let you do the right thing by accident. Almost, we don't want anyone to have to struggle to do the right thing. But there's other frameworks out there now. So one of them is Carrot. It's one of the older one. It has a more base traditional interface feel. It has a lot of features, a lot of models. It is more single function used heavy. And we have MLR3, which is another great ecosystem of modeling packages, and that one has a more Pythonic feel in the sense that the code you write in MLR3 will be very familiar if you come from a Python background. And they have a wonderful set of tools as well. And I'm not gonna sit here and say that tidymodels is the one and only approach. You can use whatever tool fits your workflow the best. I'm working on tidymodels because I feel like that is where I can contribute to the world of modeling the most right now. But nothing is better or worse than anything else. You need to use whatever did the job done for you. And that is to say, this is still a machine learning with tidymodels workshop. So it will be talking about modeling in general using tidymodels as the implementation. So a lot of packages, but the majority is done in the 5 packages. What majority of work is done in the 5 packages: rsample, recipes, parsnip, tune, and yardstick. And the way we do it is we use the tidymodels meta package. So when you load tidymodels in, it will load a lot of other packages for you. So you don't have to load all of these individually if you're working on a general problem, loading tidymodels, and it will load most everything you need. We also have some links. All these blue ones you see, the links. So if you like, so just load it for instance. There's a lot of functions across everything, and it might be hard to remember where something is coming from. But let's say you need to, if you want to find something to like create a regular grid, you can search for grid. It might not be there, but we can see where grid, and suddenly we find, oh, it's the regular grid function from the dials package. So we have these little search things, and the same thing for the model objects and the pre-processing steps. So we have, we're trying to make links to resources that help you be successful, as successful as possible. So when you load the tidymodels package, it attaches a whole bunch of packages. And we see the packages I mentioned as the tall ones. We have recipes, rsample, parsnip, tune, and yardstick, but there's a couple of other ones. And you might be familiar with some of them beforehand because we have a dplyr, tibble, tidy, ggplot, per. We have some of the general tidyverse packages, which we're loading in as well, because you end up using those a lot too, generally working with the tidymodel. So the philosophy greatly enables you to work with everything at once. You're also seeing at the very bottom, we have a conflicts session that says that, hey, loading all these packages are giving you some conflict in names. So we have the very common dplyr filter, stat filter, using the same name without doing anything. The dplyr one will overrule the stats unless otherwise namespaced. We have this tidymodels prefer function that when run, explicitly resolves some of these conflicts. And it's not required to use it, but it deals with some of these functions that appear in multiple packages. And when you're using tidymodels, we think that you will probably want these. So like the precision, retall, and spat functions from yardstick provides performance metrics. We assume if you told precision, you want to use the yardstick one. If not, you can namespace this in. So this is another way to help you deal with the conflicts of loading all these packages. And lastly, a small point of comparison. So one of the main comments with that of new users in the tidymodels is that they feel like there's a lot going on, there's a lot of functions, there's a lot of arguments. And it might appear that at first, but tidymodels in of itself is we try to write it in a fairly modular way. So you will have to use more functions to accomplish what you would normally use less functions with in a framework like Carrot. But the modularity hopefully makes you actually end up using less arguments. So basically, we're swapping many arguments for many arguments and few functions with some more functions and few arguments. So we can see that a little bit here at the very end. We're just pulling out the number of arguments, and we see that a common Carrot workflow, train control and a train default, yields you around 38 possible arguments, whereas a similarly styled set of functions in the tidymodels yields you with 23 arguments, which of course isn't a fair comparison because the type of the functions themselves also in a way act as arguments, but we hope that this becomes give you a smaller complexity. All right, so that's just a little bit introduction what we're about. We have some guarantees coming in later about what actually happens, but I'm very happy with the approach we have so far. So what we're working with today is but we need some data to run these models on, and we'll be using the elevators data set. So data package I recently created that contains all the registered elevators in New York City that was provided in a Freedom of Information Act request back in September of 2015. And there's a bunch of data in there about the elevators. We'll look at that in just a little bit. And it has been filtered and cleaned out, so it's a little bit easier for us to use. But it still is messy enough that sadly it will replicate what you might see in a day-to-day working with data. So we need to think a little bit about what's happening. And to give us a little bit of a scenario of why we're using this data, I'm coming up with a scenario that you are not a big fan of elevators, you feel claustrophobic when using them, and you want to be in an elevator as little as possible. And because you want to be in an elevator as little as possible, you would like to know how fast the elevator is going before you step into it. Because if you know how fast it's going, roughly, and know how many floors you're doing, you know how likely how long time will you spend in there. I spent some time over the years in some very, very slow, very janky elevators for residential areas, and they are absolutely terrifying. And yeah, but it's also, so that those data, I'm going to send you off to a hands-on way to work a little bit yourself, but I'm going to finish talking a little bit first, because we have our data set right here. So if you have run the installation from the website, and you download the labs Amazon file, you should have a file where you can explore the elevators data set by loading it in. You can also do question mark elevators. It has a somehow decent documentation of what each individual variable is about. It might not give a lot of information, but it will at least clear up what the variable is about. And there's a lot of things happening in here. So we have 25 variables, and they vary in degree of usefulness. So I want you to take a little, 10 minutes, and once you load at the variable in question will be speed underscore FPM, is the speed of the elevator in feet per minute, and look at how it relates to these other variables. And also think about how useful the variables will be in a situation of, I want to know how fast this elevator is going without looking it up. So like without, yeah, so you're standing at an elevator, you want to know how fast is, hopefully if we can build a mental model of how fast will this elevator be going, what information we can need. So let's take 5 minutes. I'll start a timer. Oh no. All right. All right, so we have a 10-minute timer. So let me know if you have any questions. You should be able to find all the information in the website. If not, now's the time to ask in the chat. And then after, we will go over what we found. Oh, I'm back. Sorry. So a lot of things. Main thing is we're back. Does anyone want to volunteer what they found? And either type in the chat or unmute and say it. Either is fine. Doesn't have to be any major insights, but something you find while exploring the data.
I found a few things.
All right, let's see.
Able to hear me.
You're a little quiet,
So I can just go through very quickly. Higher speed elevators tend to have a car buffer type of oil. They tend to have a safety type of F. They tend to have a machine type of GL. Capacity should be high as opposed to low, but not extraordinarily high. And also, I found something about the manufacturer. There is a manufacturer that has very high speed, or manufactures very high speed elevators, and that manufacturer is called MRL. So that's a few things.
Some great insights. All right. Thank you so much for sharing with that. I have a couple of small ones to include in the slides. For one, we have to borrow here, which is a geographical indicator of an area. So here to plot it, you can see that geographically there are, we're split into 4 regions. We can see Manhattan, the Bronx, and so on. Kind of see a little bit, like we see this little rectangular hole in Manhattan to be Central Park. And there's apparently a couple of elevators right in the middle, so there might be something happening in there as well. So we have these big geographical areas. We also have, at the beginning of the data set, we have a device number, which in and of itself isn't useful because it is a unique identifiable number for each elevator, so they would all have their own one. So by themselves, we can't use those. They're just a name of it. The BIN is a building identification number. So the building the elevators in would have their own number. And by itself, there are ways we can use it. The data set has a variable included in it called elevators per building. So it summarized from the building identification number to see, does this building have 1 elevator or 15 elevators in them? Because of course some bigger buildings, especially hotels or other conference, other types of buildings have more elevators. And that might have something to do with it too. Maybe having a lot of elevators might also push you to have faster elevators, because faster elevators and more elevators both allow for higher transportation of people. But we also have these other 5 variables right here that probably isn't super important, or at least they are also assigned to device numbering. So we have the borrow, which is divide the whole region into 5, then the attached blocks divide each of those further down, and the attached lot divides down the attached blocks. So it's, you might be able to use that geographical information, but we won't be doing it right now. It's a very highly, it splits the geographical regions a lot. Likewise, we also have like house number, street number, and the zip code. which is also identifier. Say where it is. And then we might be able to use it. This data is too messy, honestly. Like the street name, we might be able to say, oh, on Broadway, there might be a lot. But this street name variable is not super useful in its current state. And I want to thank James for helping James get everything installed. But we also have all these other variables that might have a little bit more. We also saw what Steve said. Steve or Steven?
Yeah, either.
Steven, yeah. Saw this relationship between the capacity and the speed, which then is a very good insight. It isn't when you once you see it, yeah, well, it makes a little sense because it would be crazy to have a high capacity, high speed elevator, right? So it made sense that if you're carrying a lot of pounds, it can be hard to go fast. But it still is like this relationship between them, that the smaller capacity ones can have higher speeds. So that makes sense. And that's all we have for the first one. I'm sure I still show my timer locally. Yeah. So we're done introduction, and we will go into the second set of slides. The way I found it is if you go to URL, you can slice off everything after slides, and everything after, back to the main site, click the next one. All right, so now I'm gonna share. A little speed of view for me. Yeah, a little speed of view for me. So now we looked at the data a little bit, and we feel that there might be something. We might be able to create a small model that will have some decent performance. Let's see how that works. So we need to create our models. But then in the real world, we want to spend a lot more time looking at the data, finding some of these insights. But some of these insights might not be that complicated. We might let the whole capacity speed relationship very prominent. That's something that the model will find, but we can also find it very fast. And there might be other little types of things we can find as well. But we imagine we spent some days looking at all this data, finding all its secrets, finding out where it works and where it isn't. This data is messy, there's missing data, there's a lot of weirdly encoded things in it that I have hidden some of that for you. If you really want to, you can the package also includes elevators raw, which is how the data originally came in. You can see that I did a fair amount of initial cleaning. But we have the data, we looked at it, we're fairly confident, we have an idea of what it includes, and we want to do some modeling. So there's the first existential question of what is a model? And I like to think of a model to be representing relationships. And for our specific use case, we want to represent a mathematical relationship between the outcome and some set of predictors. It becomes statistical in the nature that we assume some error in it because we don't expect to have a complete we don't expect to have a complete relationship between everything. We might could have, if we had like the model ID number, we probably would expect a different, like we probably would expect that somehow the speed of an elevator could be uniquely determined by some factors, but we don't have that right here. So there will be some error in there, but we're trying to capture a good relationship. More so, we think of a model to be consistent of two parts. We have our preprocessor and the model itself, and we want to try to split apart what happens in the preprocessor and what happens in the model. And we want to make sure we think about both of them. There's technically a third part, which is post-process, like post-processing, like post-model activities. We sadly don't have those implemented yet, but they will come. They are on a roadmap to come, but I can't give any solid dates on when we'll start working on it. But the way we're seeing it is when we're working, we have all the models being fed through a parsnip, which is the package that deals with the model fitting, and then the preprocessor of how and which variables to be included with a little bit of formula, which you might have seen before from LM and other modeling packages in R. But we also have the recipes package, which deals with this extended pre-processing capabilities. So the way I think about this separation can very easily explained is this example. So we have some data with very highly correlated predictors, and we want to fit it into a model, but a model such as linear regression would do very poorly on that because it assumes independence. It assumes the predictors to be uncorrelated. So the high correlation will mess up how we can interpret the regression model. So one thing that you can do is to apply a principal component analysis to the data, and that is typically called like a principal component regression. But the way I think about it is we're not performing principal component regression. We are first using PCA to do feature extraction, pull out the relevant features of the data, and then pass that along to regressions. Instead of thinking of it as one model, I see it as two. We see it as a pre-processing step and a modeling step. So the question then becomes, what part of this whole thing do we consider to be part of the estimation? Like when are we estimating things in this process? So the two questions is regulation data and a formula specifying what variables to include. We pass it into a PCA, and then we pass that into a least squared estimation. Then there's a fitted model. So we can either think of the estimation to only be part of the least squared estimation, or we can think of the estimation to be both of those two things, both the pre-processing and the estimation. And in the tidymodels framework, we think of this more extended part that both the pre-processing and the model fit is part of the estimation. So we like to think that like it encompasses more, and it can go wrong in a lot of different ways, and sadly it can go wrong in some very subtle ways if you don't treat it like this. So something like PCA, that those loadings you pull out will depend on the data. So if you don't include it as part of the model and do PCA and everything and then pass it in, we can do like poor performance estimations, but we also took that like subtle data leakage. And we talked about a simple pre-processing step of doing PCA, then a model, but we can have much more complicated pre-processing setups that would make all of these problems harder. And we'll talk back to that later. We will right now we'll start by talking about models, and then we will get into feature engineering later. But this is still part of the whole process of modeling, that if you use tidymodels, as I'm showing you today, you will have to go out of your way to get into problems of data leakage and selection bias and things like that, because the tools tries to set it up correctly for you the first time. We're not perfect, and there will be cases where that isn't true, but we are trying to design these tools to limit this as much as possible. And I'll try to point it out once we get to it. Before we get into modeling, we need to do some data splitting. And I already did a little bit of a bad thing by letting you explore the data on the whole data set. We'll get to that in a little bit. But we want to do a data splitting first, because the main thing, and this is one of the main takeaways you can take away from this workshop, is that you always want to have a separate piece of data that can contradict what you believe. So if you have a model and it fits one way or another, and you believe that, oh, this one can accurately predict how fast the elevator is going, you need to have some data that you can then validate. Is this model even able to? Because we fit the data on fit the model on some data. So it already knows that data. We need to do some new unseen data to be able to say if it actually worked or not. That's the main one we want to use. So we can think about this as spending. So the end goal is still to find an optimal model, and in a prediction setting, an optimal model is one that works really, really well on data we haven't seen before. It can extrapolate into unseen data. And the typical way of doing this is splitting the data into two data sets. Our training data set, which is the one we'll use, we estimate model parameters, we can pit different parameters for the model. It's the one we're working with 95% of the time. And lastly, we have our test data set, which is then used to get an independent assessment of how well the model worked. So as a piece of data I talked about right before, this data will is the one we use to validate if the model actually worked or not. And you don't want to use this at all. Like, you are allowed to use the testing data set once, which is at the very end. Once you have selected the model, you can predict on the testing data set and see how well it worked. And that's all you're allowed to do with it. Which is where we made the mistake right before of exploring the whole data set. because we are technically exploring the training and testing that training data set at the same time. But we'll be fine in this case. Yeah, so I think we are heading up at the first break time. So I'm gonna do a start a 15-minute timer, and I will see you all back here. So remember to fill up some new water. That's great. I'm gonna fill my tumbler right here with some water, so I'm ready when we come back. If you have any questions, put them in the chat and I'll answer once I come back. All right, I'll see you in a little bit. Hello? Oh, you hear me now?
Yes.
Thank you. All right, so Steven had questions about the pre-processing, how one of the safety types has very unbalanced distribution. And I'd actually show that real quick. So let's just see it by itself. So if we do loading the package and we say elevators have safety type, so if true, we are seeing a very highly skewed distribution right here. So the question that was posed is how we're handling this. And there isn't any one way of doing it. What we will probably do is to we can handle one of the ways we can handle this is using pre-processing. I will probably turn this into a vector or turn this into a variable maybe of 4 classes. So you would say it's I, F, N, A, G, or something else. So re-leveling this variable for these different types. We could, like, nothing is stopping us from building a separate model for each, but then you're losing some efficacy in other ways. So like, generally, if we just stay in a linear regression space, it would be better to keep this as a tangential variable instead of splitting into the models, because the error estimation will be enhanced by the additional observations in 1-bit model, assuming that the safety type isn't correlated with any other things. But then it is not a clear answer. I'll probably stick with one model and reformat this variable to work a little bit better for what we are trying to do. And we will get to that in just a little bit. Back to data splitting. So we know we already have to do the splitting. We need to have a testing data set and a training data set. The next thing we need is to find out how much. Because data, at least for many use cases, is a precious resource and we need to use it in the right way. So we don't want too much data in the training data set, because then we don't have any left over in the testing data set to data assessment of how well it worked. And likewise, if we have too much data in the testing data set, we don't have enough data to fit the model. From a purely statistical standpoint, you would fit one model on all the data and then use statistical methods to see how well it went. But that requires us building up the model, laying out all the assumptions, making sure we have a statistically sound model before we fit it. For non-statistical perspectives, where we just want to fit a model and see how well it works, having a separate data set helps us to do that. Generally, what we do is when we're splitting
it ends up being a 75-25 split, 75 for training, 25 for testing. You can go up and down a little bit if you, depending on how much data you have. If you have a lot of data, you could do like 80-20, because if you have enough data, then you can make the test data set a little bit smaller while still having enough observations in there. Likewise, if you don't have that much data, you might want to like increase the size of the testing data set to get it big enough to capture some of the variability while doing the assessment. A couple of different ways of doing the splitting. We can do simple random sampling. So we have two buckets and randomly put our observations in the different ones in the right proportion. We can do which words, well, there's nothing in that. It needs to be done randomly though. So we can't just take the first 70% of the data in one bucket and the last 30 in the other one, because there might be some inherent ordering in the data that will then make this split not appear random. So what we would do is have it done randomly with a seed to that reproducibility, which will then help us in the long run. We can also stratify it according to the outcome. So here we want to predict the speed. So we would like the outcome, the distribution of the outcome in both the testing data set and the training data set to have roughly the same shape. That is to say, both the testing data sets should have slow elevators and fast elevators in roughly the same proportions. And that's what we mean by a stratified sampling. Is some threads are being done to make sure that we are sampling more or less evenly. Typically, it's done in a regression type. We do like 4 quantiles, and we align at that. If we do a classification task, which we won't be doing today, but classification in many ways is similar to regression, but instead of predicting a number, we're predicting a class. And that can be like 2 or many classes. And a stratified sampling on that would make sure that the proportion of each class is close to equal between the testing dataset and the training dataset. Because it would be hard to predict a class that didn't appear in the training dataset, but only the testing, and likewise the other way around. There's also other methods. So if we have any data with a time component, which we don't have right here, there's some time data in this data set, but it isn't super useful for something like this. But let's say we had observations that occurred on specific times. Then we could do this splitting in a time-based manner by saying the 80% first observations are our training data set, and the last 20% of the observations are our testing set. That way, we are not violating any time travel ideas, as in we are imagining that we're fitting a model on a specific day and then see how well it works on data on future days. In general, there's very little downside to using a stratified sampling approach. So there's very little wrong of using it if you can. So it's not something you have to worry about. It generally provides good results. And most of it doesn't provide bad results. So before we move on, we looked a little bit at the data before, and we can do a little cleaning to it before we move on. So we load our data, and I wrote this little janky function right here that extract. So what it does, it will take in a variable, extract the first number or the first sequence of of digits, turn into integers, and then remove any really high values. And I am applying that to the floor from, floor to, and travel distance. The reason why I'm doing that, so we can say view of, by default, this data set, if we notice it, once we're working on is the travel distance is weird. It has a lot of things going on to it, but most of them appears to be feet, sometimes inches. So what this function does in this case is here, it pulls out 16. Here, pulls out 16. Here, pulls out the 9. Here, pulls out the 73, and so on. It's not perfect. It doesn't use the inches if they're there, but it's still giving us more information than what it has in its target state. I'm also applying it from the floor from and the floor to variables because they are weird too. They have a lot of things going on. So, and we have like second right here, which is still 7. So it pulls out what it will create some NAs, and it won't do everything perfectly, but it will do things well enough. Another thing in this travel distance is there's weird things like above, which doesn't appear like a distance, and there's also some dates in here, and the dates appear to be very close to the date that the data was handed over. So there's definitely something weird happening right here. Hence why we're saying if it has a really high value, we're ignoring it. But it's not perfect, but it works well enough. Secondly, what we're doing with the outcome right here is it's in a speed and it's feet per minute. But we saw that the distribution is quite a skewed distribution. There's a lot of small values at the top of really high values. To make our life a little bit easier, modeling wise, I am not transforming that down. So then we can go back here. If we say elevators, speed, and we're hitting it with 25. So originally, the outcome of a data set looks like this. A couple of elevators are very fast, but a lot of them are down low. What I'm doing is turning it a little bit less weird. So taking logarithm of it because the data isn't spread in a weird way. And we're doing that right up front. So once we did the predictions, we can take do the inverse transformation to find out what the prediction will be. This isn't necessarily a required step, but I found for what we're doing later, that'd be nice. And lastly, I am removing some of the variables we don't need. So we have device number, doesn't matter, it's ID variable, all the location-based things like building number, tax plots, house number, street names, and zip codes. We're not going to include those because they're too granular for what we are trying to do. Zip codes might not be, there might be, there's a little bit of a lot, but I kept in the borough. So the borough is still dividing the area up into 5 regions. We still have some geographic predictors in here, but we don't have that many. Once we have that, we're going to use our first tidymodels function. So we'll start by using the initial split function on the data set we just cleaned. And it's cleaned data set that we transformed to outcome. We extract a little bit more information about a couple of variables, and we remove stuff we didn't want. So now everything in the data set is something we probably want to put into a model at one point. So we use the initial split function on this data set, and it will create this split object that right now say that we have around 16,000 observations in the training data set, a little bit less than 9,000 in the testing data set, and how many observations we have in total, 35,000, and I set a seed, which means that when this split is happening, it's happening the same every single time. Then this split object, we can use the training function and the testing function on it, and that pulls out the respective data sets. So now using the training function on our split object, this will be our training data set we'll be working with for the next while. And likewise, we also pull out the testing data set. And we can see by looking at the number of rows that they match what we had earlier. So from now on, we won't touch any other data set than the training data set. So now we actually, split our data. We did some light cleaning to make it a little bit more manageable. Remove stuff we didn't need. So now we're ready to fit a model. So we can start by the small typo right here. So we're not doing housing data, we're doing elevator data. But typically, in a lot of modeling functions, uses formulas. And it is like a symbolic representation of what we want to include. So it can do a bunch of different things. We can say, if we have a model function, left-hand side of the tilde, that'll be our outcome, and then the right-hand side, we can say what variables we want to include. So here we could say, is there the read, or the tar buffer type, or we could include an interaction between them, and we pass in the data. But we also have shorthands. So if we have a lot of variables, it would be very tedious to write all the names out to say something plus something plus something. So we use a period. So speed FPM tilde period means that the outcome needs to be the speed in feet per minute, and everything else in the data set would be parentheses. And we're also allowing some inline functions. So I did the log transformation earlier. A lot of formula methods allows you to do this transformation inside, or here we're doing a 3-degree natural spline. But we can do a lot of other things in there. But by itself, it's a little inconsistent. For one thing is, it can do a lot of things, but it isn't enough. So for one thing, we can't nest all these inline functions. So that's like some problems. We can nest things. So if we can't, for example, do a PCA on a bunch of things, because we would probably need to stale the individual variables before. We can't do nesting, and everything happens at once. So even if we're doing a natural spline or we're staling variables inside a formula, we can't redo those calculations later. It can also be very inefficient, especially for wide data sets, because what this will do is many of these modeling functions will take the formula and the data set and pass them to a model matrix function that then turns the formula with the data set into a matrix that's then passed along. So there's a couple of different issues just using formulas in general. Another big problem is that not all the modeling functions that you will encounter will have a formula method. So even if you know and are really comfortable with the formula method, you can't be assured that all the models that you want to fit work with it, because some of them require the non-formula methods, which tend to be a XY interface. So it tends to be that the modeling function will have an X and a Y, where you need to pass in the predictors as one object and the output as another. And then this is inconvenient for a lot of different ways. The transformations, but on right, you have to always split out your data, because typically you will have everything in once, but now you can't put everything together at once. And it can also become a problem if the model can do both, because some of them will support XY interface and formula. So there's all types of mess happening. We're providing the third way, which is my preferred way of doing it, which would be recipes, which deals with all these issues. But for now, we need to know that there's totally different ways we pass stuff in. So going back to a simple model, so we're using a linear regression model. And we're doing a very simple model. So here, simple model, we're saying speed by the borrow and the capacity. We already know capacity has some influence. I'm putting in borrow to see anything happening in here. It probably will not be a great predictor, but there might be some big things like especially Manhattan is gonna have probably a higher proportion of taller buildings, which, so the borrow by itself isn't necessarily useful, but it is capturing information from a lot of places. So once we have that, we can look at that. But we want to see how we can do the fitting in tidymodels itself. And this is where the parsnip package comes in. So it tries to be a unified interface to modeling by giving you a one-stop for all your modeling needs. Because for one thing is, yeah, we talked about doing linear regression so far, but LM isn't the only way to perform this linear regression. We also have a GLEMnet that can do regularized regression. STAN is a whole Bayesian framework, which we can also write up a linear regression, but in a Bayesian way to perform Bayesian regression. Or we could use Keras to fit a regression used in TensorFlow. But all of these different methods have different interfaces and a lot of minutiae that you need to remember of how to use the different ones. Parsnip tries to standardize all that, and we'll see how. So the way we use a parsnip object is we start by creating a specification. So parsnip comes with a bunch of functions that we call specification functions that we use to specify something. So here we have the linear ret function, totally that gives us a linear regression model specification. It also defaults to saying, I'm doing regression, and it's using a computational engine. Computational engine is who will actually do the calculations. So before I said we have LM, GLEMnet, STAN, Keras for linear regressions. the specification right here defaults to say we're going to use LM unless otherwise told. We can set it with a set engine. The models now have default, so you don't need to set it to LM. But no, it's always that, but we're doing it for consistency. So now we have a model specification object that says what it wants to do, and we fit that one. So we can fit the specification with a formula and our data, and we did bad our a fitted model. The fitted model is very much like a normal LM object, and the parsnip object itself is very thin wrapper. So we say it's a parsnip object, and inside it has the LM object we do. So we can see right here at the output, we see that some of our intuition works well. We can see when the capacity goes up, the speed goes down. We see that the branch right here is the reference label, and we can see Manhattan. Being in Manhattan, we're expecting to go faster. Everything else especially go slower. So far our intuition works fairly well for the model so far. But where this becomes a useful, because right now I'm showing a lot of code to fit a linear regression model. But where the power comes in is if we wanted to do it's different. Let's say we wanted to do stand to run the model using a Bayesian framework. The only code we change is in the set engine. So instead of saying set engine LM, we are saying stand. We're passing it some more information about how exactly to run this one, because the Bayesian one needs to know a couple of other things. We're passing in, so you want to run 4 chains, 1,000 iterations, but everything else looked the same. We still fit this code. This code right here looks exactly the same as before. We're just slightly changing the specification, and parsnip will take care of the rest. And you can see right here that the 2 fits, they're not identical because they're trying different things, but they're still in more or less agreement. Where we gained something. So parsnip tries to make names for things that is possible, and they're especially useful for if you want to do like logistic regression. We have a function that called logistic regression instead of having to set the right linked function in a GLM. We have everything works out like that. Most of the names we're trying to do sensible names. And so for things like random forests, a lot of them you want to specify the number of trees. And we call that trees. Whereas other packages has entries, num trees, trees, a bunch of different names. If you're using parsnip, you need to learn one name, and hopefully that name can carry you through. One of the things that's happening right here is we have some duplicate transformation computations when we fit these 2 models. So like for example, the formula method we're passing in with 4 variables, 1 outcome, 2 predictors. It is taking the categorical variable and turning it into a the indicator variables. To make it into a matrix. So there is some amount of work happening in there, which isn't happening up front. So the way we did it right now was that calculation had to be done twice because it was coupled together with the model fit itself. And right here, it probably wasn't matter too much because it wasn't that bad computations, but you can imagine if we did a little bit more, we would need to be a little bit more mindful of not doing these duplicate transformations. How we are dealing with that is what we call a workflow object, which bundles the preprocessor with the model. So before we had a model object, we can now, and that wouldn't fit with a formula. We can instead create a workflow object, add in the parsnip specification, and then add in the formula. Because then we have one object that is wholly specifies what needs to be done. It's saying the engine, what calculations needs to be done, and on what. So then when we fit it, we just need the data. It knows what to do, and we can swap out the model, add, let me say, update the model in this workflow to use the stain specification, and it works just the same. Yeah. So one of the things the workflows knows how to do is once we fit the model, the preprocessor has already done everything it needs, and the model matrix is formed. So we don't need any of these repeat computations. It also helps us organizing our work in what we're doing by tightly coupling the pre-processing with the model itself. And lastly, it really fits into the philosophy that this model process includes the pre-processing as well as the estimation. So now, when we fit a model and predict on a model, that includes the pre-processing as well as the model itself. So once you fit a model, it will do the pre-processing, and then the model, when we predict on it, it knows to go through those same steps that are on the other end. So we have one unit instead of a couple of smaller ones. And the predictions work as you would expect. So we're creating some random data right here, shuffling the data framelet completely, just so we don't use the testing data set. And when we predict on it, we just predict on the fit, which right here is a workflow object. There is some data, and it will return a table. And it will always return a table. And the name it's named well. So right, if you do node prediction, it will be .pred. There is some of these models will support alternative prediction types. So with some of these models allows us to add predictions intervals, which then will return neatly. So we have to guarantee that the predictions will always be returned as a table. The column names and types will be unsurprising in the sense that if you're predicting classes, it will return it as classes, return it as a factor with the right levels. The names then will be .pred, .class, pred.class, things like that. And more importantly, the number of rows in your data, and the output will be the same. And the last one might not seem like a big guarantee, but it might have bitten you before, because some of these modeling functions, when they encounter missing data, will silently remove it. So if you have 50 observations and the 45th observation is missing, the predict method will work fine, but give you back 49 observations without telling you that the 45th observation wasn't there. It shifted everything around. We're then seeing that won't happen with always the same amount of bad, which allows you to bind bad your predictions to the original data set, like the observation by observations will always line up. And before I move on, I'm just gonna quickly address a question in the chat. So Stephen says that it seems that pre-processing steps aren't in the workflow. So that's a good comment. What I've meant so far by pre-processing steps is, and it's a fine line, so that's the reason why you're confused. Because it falls into two camps of things we want to have done when we fit the model and things to done before. So I took away some variables didn't need it. We could do that in the workflow as well. We just didn't do because we're not going to use it. So it's easier for that specific use case to remove the variables upfront than have to remove them every time we specify a model. You could pre-process the outcome, which we did inside. Generally, we don't have the facilities to do that really neatly yet. There's some use cases where it's really hard to do. So we generally recommend that any pre-processing of the outcome should then be done at the very beginning, preferably before we do the splitting. And I also did the pre-processing of that I pulled out some of the numbers from the variables. And that could have been done as part of pre-processing. I did it beforehand as part of data cleaning, partly because that is a static transformation, in the sense that it wouldn't matter when I did it, because it's always done the same way. Where it becomes really useful is when we're centering and scaling a variable. That will depend on the data question. We can't do those beforehand. But things like removing variables, renaming variables, doing static transformations like logarithms or other things, those are fine to do before. And I'll show in the next section how we will handle pre-processing. If that answers your question. If not, I would encourage you to wait half an hour and we'll get into a little bit more about pre-processing in general. Once we have these performance metrics, so I showed before how we can do predict to get back the table with the outcomes. The augment function works roughly the same way, except it gives you the predictions and then binds back the original data set. So by predicting, so you can do predict, bind original data, or you do augment that does everything at once. So we're taking our model that we fit on, taking our model in, and we'll do augment, which means that now we have the shuffled data plus the predictions as a column. Taking that, we can now calculate some of our performance metrics. That is a lot of performance metrics. So here we have the documentation from Yardstick that contains all performance metrics, and there should be most every type of metric that you will need, all organized by time. So within regression, so we have a whole list of regression metrics. So we'll start by just using IMSE, so it's the root mean squared error. So we're taking the prediction, which is out here, is named .pred, and we're taking what we know to be true because we're like assuming that, like, we have the real value. So here we have the speed in feet per minute. We're taking the difference between those, squaring them. So the root mean. So we're squaring all the differences, taking the mean of that, and taking the square root of that. And that gives us a measure of, like, on average, you will be wrong by this much. And here, results horribly bad. So it's not surprising. And this one is wrong different, but we even like shuffling on the non-lot data. So it's all going to be messed up, but this is how it generally works. We can also, instead of calculating on a one metric by one metric basis, we can treat a metric set of a handful of different metrics and apply those as we did before. And we did a bunch of different metrics. If you're familiar with the Broom package, we have allowed all the Broom tidiers to work through these parsnip objects. So here we fit a linear regression model. So even though the linear regression is inside a parsnip object or workflow object, using glance or tidy on those will still surface up what would have happened if you had used glance or tidy on the model object. And the Broom package is amazing. So sometimes your deliverable once you fit a model is to get back the estimates, parameter estimates of standard errors and p-values. Using the tidy function on that gives you just that. All right. So our hands-on. So now I want you to take, I'll show it here. So we have a labs object, and you can kind of see right here. We did the introduction, which is right here. So the next session to work on is this one right here. This is models. So there's a little session. I've already copied in all the pre-processing code. So like you run this bit one, it create the splinter if you can look at it yourself. And yeah, so just follow through and then stop by the time you hit features or by the time you run out of time. So we are actually, so this lab isn't terribly long. So I'm gonna weave it into the break, also just to make sure we get through all the material in time. So, and then 15 minutes is break and lab also. Then type in the chat and I'll help you along. If not, we will meet back after the breakdown, after the hands-on, to get ready for the next session in 15 minutes. So we have actually people left up to answer some questions. So we have we do have methods to do hierarchical. So, and that is one of the neat things about the way this package works. parsnip is there's a bunch of engines. We have a package called multi-level mod, which is if you install and load it in, gives you access to model specifications that can do hierarchical modeling. So it still follows in the parsnip interface, but instead can fit more different things. I'm not aware of how we can monitor different chains. Instead, there might be a way to, but I'm not aware of that at this moment. If you need those, what you can do is once you fit the model, so if you say extract fit engine, it gives back the actual underlying one. So if you do extract fit engine on the stain model, you just get the stain model back, and you can use whatever tools from stain to modify those. All right, I'm gonna see you back in a little bit.
Hello. All right, we're back. Still have a little bit left until the break is done, and then we'll move on to the next section. All right, so let's move on to the next section. We're not doing great on time, but I will try to catch up. All right, so next we'll talk about modeling in general, and we talked about time-lapse general. So now let's move on to feature engineering. And I'm setting a timer for the next break. All right, so feature engineering. So a lot of like general philosophical problems with this. I like to think about a feature as something that does into a model. So generally the variables we have in a data set can be thought of as features, but we can also extract it out to be anything that is being derived from the data in question. So we have a lot of other like things like interactions, polynomial expansions, in the PCA feature abstraction. There's a lot of things, but feature engineering as a technique or field sounds very cool. It's very like new hip term. A lot of it is related to pre-processing. So we generally think of pre-processing as these are two different things. So we have typical transformations we have to do over and over again in blue. These are the steps that are necessary for the model to work. So these can be transformations to the data, normalization, having all the variables to be in the same range, formatting things, re-encoding issues, imputation, dealing with missing variables. Some of these tasks are required for the model to even run. So we think of those as pre-processing in a very general term. They don't care about, it's not about increasing performance, it's about making the model run. Most of the mathematical models, other than the tree-based models, requires all numeric predictors, which we don't have. We a lot of times have dates that are also variables, geographical variables, things that are not numeric. All these blue things are things that turn something into all numeric, with none missing. And then we have the feature engineering steps, which is the transformations that give us a more performant model. So pulling out things efficiently. This can be things like ratios of different things. I like in a lot of sporting problems to find out if a goal appears, what happens or not. We can have the position of the player trying to go for a goal, and we have that information as an X position and a Y position. But what really is important is how far away you are and at what angle you're at. A model, especially a bit complex model, might be able to find that from the untransformed variables, but feature engineering would be saying, oh, this is a transformation that will work really well, that will increase the efficiency of the model. We think of that as feature engineering. One of the biggest examples of feature engineering is dealing with date variables or date time variables in a data set. So here we have the last personal inspection date. The date of the last in-person inspection of the elevator is considered as a date. So it says like when it happens. And it is, if we don't do anything and the model doesn't error out, it will be converted to an integer. It will be integer of seconds or days since some reference point, which is unlikely to be useful unless because in essence, it just becomes an indicator of age. But we can recode it in many, many different ways that may or may not be more useful. So we could recode it day since a very specific reference date, or day of the wait. What month? What did it happen in? What year did it happen? Did it have any specific holiday? Did it happen? And if we have a date time, even we could say, is it close to lunch? Is it before lunch? Is it after lunch? Those questions, depending on the variable, but those types of information can be very valuable for our model to be able to pull that out. And that is like an example of feature engineering, knowing something about our target we're working on, pulling these things out. Here, it probably doesn't matter. But here, the speed of the elevator probably isn't related at all, or at least very little, to when it was last inspected. There might be, we could maybe imagine that the elevator becomes slower since the reference date, but then we don't have that information in there. So here it is to be useful. Other times, these date time variables to become some of the most important variables in the data set. So general definitions are data preprocessing, which is the steps we need to take to make the data run successfully at AI without error. And feature engineering is what we can do to the predictors to make the model work better. It can either be by pulling out a relationship that we know is in there that the model would have to work really hard for, or pulling out things that the model wouldn't even be able to handle, even things like decorrelating variables, something like that. So we'll be using the recipes package to do that. So the recipe package is a wonderful package that part of the tidymodels, which helps you to do data pre-processing. So it's extendable, and once you see it, hopefully you'll agree that it works fairly intuitively. So I think it's easy just to let it show. So start at the very top, we take our training data set, passing it into a recipe, and then we use a formula expression right here to say speed is the outcome, everything else is predictors. And it's partly why I removed all the unneeded variables earlier, because either I have to write an annoying formula right here to exclude them, or I have to remove them later. So just by creating this is the specification saying on a recipe, but this is this. And we can see we have all the variables in it, what type they are. So we have like nominal, date, numeric, and what type of role they have, and the predictors or outcomes. Then we can start by working with the dates. So we start by, after we specify the recipe, we say we use the step date function. So a recipe function that says on the approval date and the last inspection date, extract some date-related information. So it will, by default, extract out. Let's just we naturally find out. We say recipes. reference step date right here. So by default, it pulls out the day of the week, what month it is, and what year it is from the data set. And so it for each of these ones, it would pull out the day of the week, the month, the year. Day of the week comes out as a factor. So it will take two variables into 6 variables. And here we are specifying that approval date and last person inspection date should be removed. So we don't keep them after this step. Step date and a couple of other time related steps keeps the original data. So here we just remove them outright. Then we want to deal with the missing data. So I'm saying we want to impute all the numeric variable, all the numeric predictors by with the mean. So if all the numeric predictors at this stage of the pre-processing step, calculate the mean of the non-missing data, and we impute the missing values in with that. Then we are taking all the nominal predictors, so that will be our characters and factor variables. If it sees a missing data, it will replace it with a factor level called unknown. So instead of having missing values, now we have a different label for when they're for. So now it's a full factor, nothing missing, just indicates when it happened. And lastly, we have a step that will take any new unseen observations in and say, oh, you're novel, you're new, I haven't seen you before. The reason why that's happening is, imagine you fit a model on some training data set, and we see some, let's say we included street names. The street names, and it made a factor variable for each of those. And then we fit the model, works really well. Then we get some new data in, and we pass in, and we have some streets we haven't seen before. If we didn't use step novel, some models would error out, saying, I don't know how to deal with new street name, I haven't seen it before. Step novel rectified that problem by relabeling everything that haven't been seen before as new, once you reapply the recipe. So generally, it's a good thing to have in non-factor variables to stop the model from complaining in the long run. And we have these neat little selectors. So right here, up here in step date, we specify the name directly. But we can also hit out all numeric predictors or all nominal predictors, which is great because step date returned nominal predictors, because it returned day of the week as a factor. So when I say step nominal predictor, it applies to whatever came out of step date. So because since some of these steps can create variable by themselves, having these more general selectors allows you to write more, but you don't need to remember what the names of them are. So you get some ease of use right there. Then we're adding on step dummy. Step dummy right here takes a factor and character predictors, traits binary indicators. It will treat dummy variables, not one-hot variables by default. We have an option for that, but it defaults to traditional dummy variables. It's not the only way to turn categorical predictors into numeric columns. There's a lot more, and you can find those on the reference documentation. we had a help right here. So one of the things it will know too is it remembers what levels there are. So it knows, oh, I keep these factors. So even when we predict with it later, it knows what possible values it has. So it knows how to create the right matrices moving forward. Some models also complain about constant constant columns or zero variance columns. So a column in the data set that all has the exact same value. We want to remove those for two reasons. Firstly, it doesn't give us anything. So like if a value is always the same, it doesn't help the model distinguish anything because having only seen one value. And secondly, and more importantly, some models will error out if it is being fed a constant column. So here we're using a step CV for zero variance, and it's applied to all the predictors, and it will flag any predictor, zero variance, and remove them. And then once we done all of that, we will normalize all our numeric predictors. Generally, we want to do it after removing zero variance because you can get problems by trying to center and stale a zero variance predictor. And it will stale and center the numeric predictors so they have a mean 0 and a variance of 1. They might not be normally distributed, but they will all have the same mean and variance. And they and we can do a couple of other things. We can also here, not a big deal, but imagine we had a lot of correlated predictors right here, which we might have because we have distance traveled and we have the highest floor. And we'll probably expect those to be fairly correlated if they're coded correctly. Because that would be like 10, 15, around 15, 20 feet from floor to floor. So the highest floor and distance travel is probably going to be fairly linearly correlated. Some models don't like that. Many different ways of dealing with it. One of the ways is to do a correlation. So it will recursively remove any variables until none of them have a Pearson correlation of more than 0.9. Other things we could do is, which we won't be doing today, but just as an example, we could also add a PCA step, which would take all the numeric predictors and calculate our PCA features. So what happens right here is, right now we just created a specification, but recipes are still estimated. So we put it into a workflow and we fed it. Once it's being fed, it will go through the steps one by one and perform these calculations. But it will keep track of the sufficient information. So everything it needs to be able to redo this again. Like it will look at the levels of the factor, or like if you're doing a step dummy on, let's say, safety codes, and it has 5 values in the training data set. Once it gets to the testing data set, they might only have 2. The recipe will know, is this one used to have 5, so I will create the 5 dummy variables, even if some of them weren't there, because I want to make sure that I'm producing the same type of output as I would have given from the training data set. If something was denoted to have 0 variance, it will be removed when we apply it later, when we predict with it. when the normalization, to normalize in this setting, we would need to know each of the numeric variables' mean and variance, because we will subtract and divide by those values. The recipe will teach us that information to reapply later. And that is the same for most of the recipe steps which are trained. Some of them are not. So some of them, like pulling out the dates and stuff like that, that is a deterministic. So that doesn't matter. That doesn't use information for training data set, but some of it is. So our recipes follows this strategy of everything that we're estimating happens at the same time, including the preprocessor. Once we have our recipe, we can add it to a workflow. This workflow, so we take our linear specification and we add our elevator's recipe specification of add recipe. So now our workflow say the preprocessor is the recipe, the model is linear regression. In the preprocessor, we are doing these 8 different recipe steps, and once that's done, we'll fit a linear regression model. And we can fit it. So we say our workflow, and we fit it, and it's the same. It'll do everything. Now this one suddenly has a lot more, quite a bit of fit, because we create a bunch of dummy variables and do a lot of other things, but it works the same as before. And it predicts just the same. So the recipe calculated all those sufficient information and then use those to reapply the same transformation to any new unseen data. Because we want to do this to minimize any data leakage. So if we are scaling a variable and we are subtracting the mean, we need to subtract with the mean of the training data set, not the, so we can't use whatever values are in the testing data set. If you want to look a little bit around, we also have some tidy methods for the recipe. So if we tidy a recipe, it will give us some rundown of what happens for each step. So we have step 1, 2, 3, 4, 5, so on, what type of operations there are, and everything we do. Once we have our recipe, that's our workflow has been fit, we can extract out the recipe and tidy that one. And that would do the same as over here, except the trained would have said true, because it has already been trained. By setting the number in here, we're filtering in. So here, since we're saying number equals to 7, we're pulling out what's happening in the normalized one. And it prints out a table of the information. So we can see that the mean of the distance traveled is 52.2. The mean of the approved year date was 2003, and so on. So it has information, so we can still pull out and see what happens everywhere. And it has mean and variance. So they're coming one after another, because it's a long format. So, but you can use this tidy way of doing things on the other one. So if we applied it to step on this set number equals to 6, it would show a table of the variables that were removed because they had a 0 variance in the training data set. Lastly, we have a little debugging information. So 90% of the time, I encourage you to use a recipe in a workflow to estimate it and apply it. Sometimes there are if you error, sometimes you're able to estimate the recipe by itself. So you can use the bait function, which is analogous to fitting it, to estimate what happens, and this will return a fit recipe that you can then. Oh no, this one's no. You're prepping up here, and bait now. So it's called prep. So PREP is analogous to fit. Baiting it is analogous to predicting. So you can use a recipe by itself, but most of the time you want to use it as part of a workflow as a preprocessor. Other fun facts. Once we fit a workflow, so let's say you have a workflow and you fit the workflow. Then you can update the model to that workflow and it will change out the model specification. If you then try to fit that workflow, it doesn't refit the recipe because the recipe is, or the preprocessing is independent of the model. So you don't have these repeat calculations going on. We have a link to all the known steps. Some of the steps can be stepped, which means that they're only applied, sometimes not applied all the time. It's not something you really want to do manually, but it is worth noticing that some of them, we have a vignette on that tells you about how to use it. It's mostly for certain observations that you, certain times you only wanted calculations to happen one way or another. The order matters. So the way we lay out the steps is when things are happening. Once inside recipes, it eventually boils down to a for loop. So do everything in the first step, then everything in the second step, and so on. There isn't anything major about it, but it's a couple of things. So here we have a vignette about recipes. At the very bottom of it, there is a recommended ordering. It's not absolute. There's definitely many ways of it. There's definitely not everything is like needs to follow this outline, but it was. This is like the starting point. So compute first, handle factor levels, so on and so on. And some of it does matter. You need to handle factor levels with number 2 before you treat dummy variables number 5. But there isn't any concrete ordering. But like something like imputing, like dealing with missing variables, generally tends to happen before most other things. Most other things can handle. Well, sorry about that. I lost myself right there. All right, about as with Parsnip, Parsnip has a number of different model specifications. It has extensions. So Parsnip has extensions for like tree-based method. We have like for hierarchical methods, stuff like that. Recipes was the same way. So there is a number of extension packages that tries to do specific things. That works the same way as in-package steps, but are divvied out to other packages more for like management reasons. So like embed can deal with embedding territorial or numeric variables down. It's a suite of different methods that will deal with turning territorial or numeric variables into a smaller, hopefully better set of numeric variables. Time TK has time tooltip package, deals with some time-based pre-processing. Test recipes extends recipes to work with test pre-processing. I'm giving a talk about test recipes and what's new in it once the first day at the conference. So if you're around and interested, take a look for that. The famous package has steps to that lets you upsample or downsample or create synthetic observations as a way to deal with an imbalance in a data set. And Julia and I wrote a book that talks about test pre-processing in a supervised machine learning sense, uses test recipes and tidymodels and Terrace. So a bunch of different ways. We also have this simple dplyr steps. So sometimes like you know what you want to do, you need to step mutate. That will work too. I'm going to step this hands-on just for time. I just want to make sure we get through all the material. So I'll do that and we move on to the next set of slides. Now, so we talked about a building. Ooh, I need to do this. All right. So we have built models. We fit. We know how to fit models using different engines. We know how to pre-process the data correctly, and we want to find the best model for our different tasks. The problem is we can't evaluate how well the model works because I told you even earlier that you're only allowed to use the testing data set once. So what do you do? So one way which we use a lot in tidymodels is to use resampling to help estimate performance. So first of all, we need to ask the main question, which is what is resampling? So for resampling is we normally have a training and testing data set, but we can use the testing data set. So when we fit a model on the training data set, it doesn't work. We can't see how well it works without touching the testing data set. The way we did around this is we create a number of resamples from the training data set that creates a number of what we call analysis and assessment sets, which are very similar to testing and training data sets. So essentially we create, like here we have B resamples. So within a resample, we have some observations in our analysis set that we fit a model on, and then we predict on the assessment data set. Once that's done, we look at the performance, see, oh, it did so well. We repeat it for all the resamples, and hopefully it gives us an idea of how well our model is performing without touching the testing data set. Here's another diagram of how we do. We have analysis set and our model, which is inside our workflow, that the fitted one with the predictions from the assessment, then a performance metric. We can then do this for all the resamples, and then we did an estimate of the performance that this model would have. One of the resampling methods that we'll talk about today is V4 cross-validation. So the way it works is we take our data and split the data into V roughly even buckets. We call the folds. And the way we create each resample is by taking one fold and say, you're the assessment set everything else would be the analysis set. So we fit it on v-1 of the folds, predict on the last one, and then likewise we then create that way we have b different resamples. And we define performance. That's all of the things, and we should talk about this at length. So, but let's show it visually a little bit first. So imagine we have 30 observations, which is too small for most tests, but it plots well. And we're doing a threefold cross-validation, and then too small, but it plots well. So we're taking our data, randomly giving it one of three colors. What we then have is, in our first fold, first resample, we fit the model on all the yellow and blue observations and predict and estimate the performance using the green. In the second resample, we fit the model using the green and blue observations, estimate performance on the yellow, and in our last fold, we fit the model on the green and yellow, and we estimate performance on the blue. This way, and then once we have the performance image, we take the mean of across all folds. One of the nice things about doing it this way is that every observation is used exactly once to estimate the performance. So that you have there's an evenness in how it works. No observation, if one observation that might be like really, really bad isn't appearing multiple times, inflating the data. So that's like really nice for that. And what we did out of this is producing a single estimate of the performance of the model. And even more, this v4 cross-validation, if we do it correctly, will be an estimate of how well the model will perform on unseen data. So in essence, the mean of the performance metrics within that is an estimate of what the performance will be once we apply the model on the testing data set. So like it's great for that. We end up creating a bunch of small models. So in the previous slide, we have fit 3 models, one for each fold. We don't keep them for the end. The only purpose is to facilitate the calculation of the performance metric of the one fold, but afterwards they are being thrown out. So it's only being, so once we do all of that, then we can fit the final model, all the training data set, and then use that one. We don't use any of these intermediate resampling models. So why do we do it? So we use the v4 cross-validation function on our training data set, and it will create a folds object. So here we have the fold object is the tuple of the indicates what happens where. It defaults to 10. It's a very good default. You have to have a good reason not to use 10, which is far beyond what we have time to talk about for this workshop. 10 for 12. And we kind of look into see like, so because each individual split is technically very similar to what happens in one of the initial split objects. So we can like filter it out, you see same analysis assessment thing, and we can pull everything that out, how we could before. So once we have that, we want to fit 10 models, one for each of these folds. These datasets will be slightly different, hopefully not too different because they're all like sampled from the same overall dataset. They will each produce a separate number of the RMSE. We then set the average out to estimate how well will we do later. So what we will be doing, we will take the workflow we created earlier. The workflow includes the little bit more complicated recipe pre-processing step and a linear model. We created the folds to fit everything through. And then we're using the fit resamples function. So we use the fit resamples. We say, I want to fit our workflow across the elevator's folds. And then I'm adding additional control, which you don't need, but you can pass in some additional arguments by creating this control object. And once you do that, you get back this monstrosity. It has a lot of information in here. So before we had the splits column and the ID column. By running a fit resample, we appended the metrics, nodes, and predictions. If you haven't already seen this before, that is a list columns. So it is a list of 10 tuples. But we have seen that before, and we have functions that deals with this. So if you want to know how well the model performed, take the resulting outcome and use the collect metrics function. The collect metrics pulls out what the RMSE is. It also calculates R squared by default. And yeah, it pulls it out. And here we did an RMSE of 0.38 on average, which isn't too bad. We can also, if we really want to, we can do the whole lot predictions as well. But since we set predictions equal to false, we can pull those out with those, see how it actually did for different observations. Having these whole lot predictions also allows us to look at how well the model performed within the different folds. So here is a little smaller than I would have liked. But we can see like the prediction and speed is fairly well. It appears to really want to predict, that it really predicts speeds between 2.5 and 7.5, whereas the actual speed of some of these are a lot higher, a lot smaller, but our model pretty little smaller, but we still definitely see it's not doing something, but it's not having perfect performance. Some notes is the way these models are fit is everything is done independently of each other. Each of these folds don't require any information of any of the other folds. So all of this can be done in parallel. That's the blue thing right there is a link that shows you how to set up everything, and it's fairly simple too. So if you need to go in here, it's small. So a lot of it is just but we're using, everything is set up for you to do. Yeah, so right here, like you just say do parallel, register it to let it work, and just run your tidy models code, and it will know that it wants to be done in parallel. There's links and more in there, but it mostly just works. We can save the individual models if you want to, so we can like expect what happens, especially useful if you see a bit variation in the model performance for each fold. So if all the models are fairly similar for each fold, it's probably pretty good. But if one of the models performs really weirdly, you can have them saved to then pull out and inspect to see why you perform weirdly. Yeah. So now's the time for the break. Something start our break. If you want to, it's technically time for hands-on. So you can like continue with the hands-on if you want. We sadly don't have time for that. So I'll come back in 15 minutes with your last set of slides. I'll stay around if you have questions. So you can do hands-on at your own leisure if you want. If not, I will touch base around a little bit after if you have questions. I'll see you all in 15.
All right, we're back from the break. We have a I'm sorry. So, Steven, I just came back from the break. See that. If you can email me after the white shop with like the specific area you're dating and like the code that you used to, that I can try to help you resolve it, because that error shouldn't occur for you. We're moving. So now we're moving into the last session of the day. We technically only have 20 minutes left, so I'll try to stay within that time slot. And do not mess. All right, so now we built. We learned how to build models. We learned how to do pre-processing well, and we learned how to fit models within resamples. We can fit models within resamples to estimate performance later on. But we also might need to do some tuning. So some of these models or pre-processing steps will have parameters we can't calculate directly from the data. So like for the linear regression model, we have an intercept. Intercept can't be derived directly by a model like k nearest neighbor. Has the k as the number of nearest neighbors as a parameter that can't be derived directly from the data. You'll have to fit the model multiple times with different values of k to find out which one performs best. Likewise with random forests or decision trees, you need to find out how deep the trees you need, how many trees you need, and so on. So there's many different parts of the model specification, both the model and the pre-processing part, that has options that you can't optimally choose just from looking at data. You will need to fit the model multiple times and find out if it performs best with either one. So a bunch of different ways of doing it. So the main approach of how we do this is to try different values, fit the model for different values, measure performance, and see which one's best. And that's more or less it. So we can do this in two different ways. We can either do a grid search, where we pre-define a set of candidates to try. So we have like number of trees and the depth. We can find 5 different values of each and then try the 25 different combinations of those values. So we predefine everything else. We also have, and they can work fairly well if you made a good grid. We can also do an iterative search. So the iterative search works by, you probably do a handful of different pairs, and then dependent on the performance at those pairs of at those different parameters, you pick new points around that, and then you try it's like you're searching a little bit. You're like, you see, oh, it works really well when trees are low, but what if we mess with another one? And you like slowly move around trying to find a minimum, and hopefully like a global minimum. If you want, tidymodels R has a great one, so it has here. I'm posting the chat right now, or you can also see it too. We have chapter 13, beautiful grid search, and chapter 14 yields with iterative search. They're both non-exhaustive, but it is like the two main ways of trying out a lot of different hyperparameters. And we are using resampling. So we want to fit many models and see how they perform. And some of these many models will be different values of these hyperparameters that we are trying to tune. We'll be using resampling from the last set of slides to do this performance. So we're doing that way. So let's say we want to have 25 different hyperparameters to choose. We set up a grid of the different values, and then within each fold, we're fitting 25 models, one for each set of hyperparameters. And getting the performance out for that, and then the summarized value for each combination can help us choose which combination of values, like which hyperparameters to hit. We'll do a twitted sample for the. Never mind, it didn't show up. All right. So the way we'll do this in practice is we have our recipe and our linear regression model. So we have our elevators workflow that we've been working with so far. We will make a few changes. So first, we'll change the engine. So it used to be the LM engine. Now I'm changing it to the Glemnet engine. The Glemnet engine allows us to do a regularized regression. Basically, it's an extension of the linear regression, but a certain weight is applied to the parameter estimates to try to give them smaller magnitude. So it's a way for us to deal with possibly many variables by saying, because the model can say, oh, you're not giving me enough to justify not having you set to 0. That's but more like theory around it, but essentially it can do variable selection for you by trying to give you a simpler model by setting some of these coefficients near 0 or at 0. The Glemnet regularized regression comes with two hyperparameters we can change. So it comes with penalty, which the amount the model is penalized for. It said this is not important. Higher values of penalty, well made. More coefficients pushed towards 0. Lower values of penalty. Well, if it's low enough, we have a linear regression. If it's too high, then there's no variables left. So there's something interesting happening in the middle. There's no way of finding out what that value is beforehand. The mixture is because Glemnet can do a combination of a lasso regression and a ridge regression, which is two different types of regularization. So the mixture can say, give me 20% ridge penalization and 80% lasso, and it will work it out. So we want to work with those two. So we are saying, hey, I want these two values to be tuned. So we're setting these two arguments in the linear regression function to be equal to tune. And that's it. So we're saying, so now then setting these to tune means that if you try to fit this model up, it won't work because it don't know what these values are. But the later functions will know, oh, I need to be tuned, and knows how to deal with it. Since we're tuning the penalty, we're no longer removing correlated features because now the slightly more advanced model works better for that. We're not going to do it, but I just want to show that tidymodels as a framework allows you to also tune variables like arguments inside a recipe. So not only can we tune the penalty and the mixture of the linear regression model, which will also tune, if you wanted to, the number of degrees in an actual spline of a variable or something like that. And there's many things in the recipes as well that we can tune. We don't have anything to tune right now in this simple one, but you're not restricted to only tune hyperparameters in the model. So grid search is the most basic way of doing it. It can be very effective. tidymodels has information about a lot of these tuning parameters, so it knows a lot of stuff. So let's see how it works. We take our workflow and we use the extract parameter set for the aisles, and it gives us back it's a parameter set that has 2 parameters. So that function, it knows that this workflow we just defined has penalty and mixture set to be tuned. We can then take that, pipe it into this grid lattice hypercube object function, and it will give us what's called a space filling design. So if we just done a grid of all the unique values, it would give us like a regular grid, everything would line up very neatly on grid points. The space filling design, which I can kind of show right here, tries to put these observations in to explore this place in a neat way. The points don't overlap that much. They overlap less than what they would have done had they been normally distributed. Uniformly distributed. And note, for example, right here is we didn't specify anything, but the functions knew that the mixture had to be between 0 and 1, and the penalty right here is actually on a large scale right now, because the amount changing the penalty, you have to think how much effect it has tends to be in a large scale. So adding something doesn't really do much. You kind of want to double it to see a change. So having penalty in a large scale right here means that hopefully we have to explore less values. So this is really good because it allows us to try a bunch of different values and hopefully don't not hit something. There's a lot of talk, but even though like if we do, there still is like some areas of emptiness. But if we look just from the mixture perspective, most values have been tried, and from the penalty perspective, most values have been tried. So whereas a grid, if we did a grid, those like with 25, we would only have tried 5 different values of mixture and 5 different values of penalty, which probably wouldn't have, which would have left us with much more room to not hit it. Like let's say mixture worked really, really well at like 80, and it just happened not to be like one of the, if we had done the regular, it would only have hit 10, 75, 50, 25, and 0. It would never have tried like 85, where here in the space filling version, it is trying 85. For technical reasons, we will stick to a manual grid because GLEMnet as a function, as a package, the way it has implemented this modeling procedure allows you to it can basically calculate as many penalty values as once. So right here, I'm creating a regular grid with 10 different mixture values and 50 different penalty values, but we only have to fit 10 different models, because from one model fit, it can predict to any 50. It can fit all the different types of penalty at once, which is really nice. So for time reason, we don't actually need to fit 500 models right here. We just fit 10. So this method end up being more performant than the space filling design we saw before. But this is a unique case. Most models tend not to have this feature of being able to fit for multiple regressions. You need to actually fit a model each time. So we saw earlier how we can use the fit resamples function to fit resamples. The tuned grid works basically the same way. It works similar as before. We're passing our object as a word flow, passing the resamples. The only difference is that we are also passing in the different grid values we want to try. And then, well, we can pull out information, but one of the things we have is this autoplot method. So if you put in a pass in the autoplot method, it will try to visualize what's happening right here. And so let's take some time to figure out what happened. So we're seeing a faceted grid. Along the x-axis, we have the amount of vectorization. On the y-axis, we have the performance metric, and the color denote the amount of penalization. So what we are seeing is, if we go from left to right, at the left, the performance is the same, which we can interpret here as the performance, like the regularization of the model might have removed some of the coefficients, but it didn't affect the model. Then at one point around 1 to the power of -2, the amount of regularization becomes so high that it starts removing so many variables that the performance goes down. And that's why we see like the R-squared goes down, the IMSCs goes up, because we're starting to penalize too much. And we can see color-wise, the low amounts of, once it goes too much, the low values of like the low amount of mixture works well, where the high amount like doesn't do that well. So here where we found that there isn't necessarily an optimal value of the penalty. Like we have like a whole stretch of optimal values, but there isn't like a bump of this is perfect. We can also collect all the metrics out in a data frame format. So we can see it just says the information we saw earlier, but in a more different way of saying, we can see what the penalty was, mixture, and what the value of the different metric was. We can do it unsummarized as well, so we also get the value for each fold, where the summarized, which is the default, takes the mean across the folds. And we can put that out like which one's the best. So here we can say it's like show the best. I'm gonna say let's show me the best of the IMSC. Which combinations give me the best of the IMSC? But as we saw with the autoplot, we have many different pairs with the exact same performance. And we've seen it right here. They all did a mean of 3.378, which isn't late. And we can even see that the values of the penalty and the mixture is jumping all around. It doesn't appear to be any global minimum or maximum. A minimum here for the IMSC, but it's just a long plateau. So what we can do instead, which is a little bit like better, is we can use this select by percent loss function, which is worked really well for situations like this because we have a plateau. So essentially we have a lot of different values that all give the same performance. So how do we pick the best of that with all the same performance? What we can do is say this select by percent loss selects pitch the model that's the most simple, where we don't lose too much. So essentially, if we go back to the visualization right here, we are telling the function, like find the best value. But right here is all the values in like the 75% the left of the stream right here. And it's saying go right until you lose 1%. Like until you lose like 1% or like performance. So like you're optimizing over simple models. Simple models here on the right hand side because they have more they have fewer non-zero coefficients, but we're still doing right and a little bit more right. And hopefully that's it. So we found a optimal model right here but any of the models are like on the left-hand side of this line perform equally good. But this one is the simplest model that only loses like 1% loss. Then in here we said that we took that and so we said and we say decrease the penalty because you need to know which direction is the simplest. Tidymodels doesn't know that by default, so you have to say you need to decrease the penalty is like the right way. So sometimes you need to like try both ways to really remember which way is which. And it is saying, oh, you want this penalty and this mixture. Update. So you take the workflow, then you finalize with that table you just created. That will fill in the places where before it's tuned with the values from before. And now we can do our last fit. So we take the workflow and we do the last fit, and here we can actually pass in the split object we created. So it passes in the training data set and the testing data set, and it will fit the workflow and do the predictions and everything we need. And we can collect the metrics. So we have our performance on the testing data set to be 0.379. And we saw that the resample result we did not that long ago was very close. We're like well within like we peer tested on the resampling well. We got a good estimate of how well it performed. And here we have the performance of our final model. Find a little bit simpler model. So maybe it has a little bit more performance than the simple linear one we did earlier, because it was able to remove a lot of the bias we saw earlier by being forced to incorporate everything. And yeah, that is all I have other than the hands-on. Sorry if it became a little rushed by the end. We have many more materials. So you have all the slides, you have the lab that is somehow annotated throughout for you to work through on your own. We have tidymodels.org. Tidymodels.org also has many articles to learn from. There's the tidymodels of R, but coming out soonish. I think basically always into print. Now it's just you can buy it, order it, whatever. You another great way of learning is you can go to Julia Sildy's blog. She tries to put out blog post weekly with data set trying to show how to use different tools, and there's so many examples. So there's a lot of happening here. And if not, that's all I have for you today. It was a pleasure. I don't know how to stop. I don't know how to stop sharing. So yeah, So thank you. If you have any questions, you can email me, and I'll happily answer. I hope you learned something. I hope you enjoy the rest of the conference. All right, I'm gonna log off now.